as I discussed in Rod's law, there are conditions for Rod's law in two conditions. One is the volatile and other is non-volatile solute. And when I discuss one graphical parts, that graphical parts you see this diagram number 1, according to the Rod's law, if any solution which obey all these three conditions, condition number 1, condition number 2 and condition number 3, the solution is said to be ideal. So on that basis, how we distinguish the ideal and non-ideal solution? The solution which obey the Rod's law, that is the PA equal to P naught A X A and PB equal to P naught B X B. Second condition, the delta mixing enthalpy, that is the change in enthalpy of the solution is 0. Change in volume of the solution is 0. Fourth condition, the interaction between the component are similar to those in the pure component. So if any solution which obey these four conditions, they are said to be ideal solution. And generally it is observed that in a normal condition, no solution is ideal, but according to the Rod's law, if they follow these conditions, they are said to be ideal. But the second part is the non-ideal. Very simple is, do not obey the Rod's law. The first condition, PA is not equal to P naught A X A and PB is not equal to P naught B X B. Del H mixing is not equal to 0. Del H mixing, change in volume is not equal to 0. The interaction between the components are different from those of the pure components. So these four conditions, if you recall, you can easily say what are the conditions for ideal and why the general solution are not ideal. The reason is 4. But again we discuss how and when the solution is said to be non-ideal. It divides into two parts. One reason is positive deviation and other reason is negative deviation. So if you understand these conditions, you can easily explain why normally the solution is not ideal. AA is one component, BE, BB is the second component, and it makes a solution AB. So if the A-B interaction in solution are weaker, then what happens? The escaping tendency of A and BB are more. These are the reactant parts, these are the products parts. So what happens? What the changes are there? The PA is greater than P naught A X A. PB is greater than P naught B X B, and therefore the total pressure is greater than P naught A X A plus P naught B X B. If you again I repeat the conditions, if A-B interaction in solution are weaker, then only the escaping tendency of A-A and B-B is more. When these conditions, the PA is greater than P naught A X A and PB is greater than P naught B X B. Similarly, at the same conditions, del H mixing, that is the enthalpy change, is positive. And here delta V mixing, that is the change in volume, is also positive. You see, if you just see one example, you can easily understand what is the reason. The ethanol, a mixture of ethanol and cyclohexane. Now, in case of ethanol, you see, there is a possibility of hydrogen bond between these two molecules of ethanol, because ethanol is the reactant parts, and cyclohexane. When we mix these two, they have break this hydrogen bonding. So when they come together, the escaping tendency increases. Similarly, acetone and carbon disulfide, benzene and acetone, carbon tetrachloride and chloroform, ethanol and water. Now, one question must be come in your mind. Why delta H mixing is positive when the escaping tendency is there? It is endothermic in conditions. And that is the reason these two conditions, del H mixing and del V mixing, are positive. Now come to the second parts, negative deviation. If the interaction of A-B is strong, what happens? The escaping tendency of reactant are very, very less. Condition is very clear. If the interaction between A-B are strong, escaping tendency of A-A and B-B are very less. In that condition, PA is less than P0 AXA, PB is less than P0 B XB, and the total pressure is again less than the P0 A XA and P0 plus P0 B XB. Here del H mixing, enthalpy change by mixing of the component is negative, and del H volume change is negative. Here again you see, when there is no escaping tendency, they are exothermic in nature. And if it is exothermic in nature, delta H must be negative and del V is negative. See example, acetone and chloroform, chloroform and diethyl ether, chloroform and nitric acid, acetone and aniline, water and chloroform. So when non-ideal solution shows the two conditions, one is the positive deviation and other is the negative deviation. If you understand the conditions, you can easily explain, and that can be easily explained by graphical. If you compare the three graphs, one is for the ideal solution, other is for the positive deviation, and third one is the negative deviation. You see, in all the cases, the red line is indication of a ideal behavior, but there is a change in graph which easily explain why they shows a positive deviation and they shows the negative deviation. The last topic of this part 3 is the azotrophs or constant boiling mixture. Actually, azotroph is a Greek word that's meaning is very simple, boiling without change. Now, if you take a solution, that is the liquid mixture, which boil at a constant temperature and can distill unchanged in composition, the solution is said to be azeotropic mixture. Now this azeotropic mixture again divided into two parts, minimum boiling azeotrophs and maximum boiling edge drop. As I already discussed, that's positive deviation and negative deviation. Those solution which shows the positive deviation come under the minimum boiling edge drops, and those solution which shows the negative deviation, they come under the maximum boiling edge drops. Now this can easily understand if you see one example. The pure ethanol cannot be obtained from rectified spirit. The reason is constant boiling, and it can be easily understood if you see the example of the positive deviation and negative deviation. You can also give the idea that's how we explain the minimum boiling edge drop and maximum boiling edge drop. Thank you.